Hello and welcome to video lecture number 7, which covers section 1.4 day 2 functions. As always, please take a moment to read today's objectives. Example 1 reads, for each function, find all x values for which f of x equals 0. Now, if you remember from the last lesson, f of x is a function notation, and in this case, it means nothing more than y equals 0. So what is this essentially asking us to do? Let's go ahead and write the interpretation of this so it's easier for us to actually complete. So what do the directions in example 1 actually mean? Well, if you read what I've written here, it's basically saying find all the x values for which y is 0. Now, if you have a point where y is 0, remember that is simply just the x-intercept. So all this is asking us to do is find the x-intercept. Now, you've been asked to do that already in previous lessons. You just have to recognize you may be asked to do the same thing, but it may not be worded in the same exact way. So I will try example B with you, and I would ask that you try example 1a. So the first thing that we're going to do is we're going to let f of x equals 0 or y equals 0. So it's important to note that you replace the entire f of x with that 0, and then we rewrite the right side with x squared minus 7x plus 10. So I went ahead and solved this problem, and notice that in order to get x alone, since you have a quadratic that has both x squared and x, we're not able to just square root to get our answer. Instead, we use a technique called factoring. And the way I factored this trinomial, since it has 3 terms, was to think what two numbers multiply to 10 and also add to -7. You may hear me refer to this as factors of C sum to B, and those two numbers are -5 and -2. Once we get there, we split the equation apart into 2 parts, x minus 5 equals 0 and x minus 2 equals 0, and from there we simply add those values to the other side. So in this case, there are actually 2 x-intercepts, and those points would be 5, 0 if I was looking on a graph, and of course 2, 0. So here are your 2 answers for 1a. Please take a moment, pause the video, and try example 1a on your own. Now notice it is not a quadratic, so it will not be solved in the same way I solved 1b. Example 2 states, for the given pair of functions, algebraically find all x values for which f of x equals g of x, then check your answer graphically. Well, after reading that, we need to determine, well, what is this really asking us to do? So the f of x equals g of x is simply saying, where are the y values of these 2 separate equations going to be equal? And those will be equal at certain x values. So what is it asking us to do? So it's asking us to find all x values that make the y values in both of these equations equal to one another. Now, what would that mean if we looked on a graph? Let's write that in next. Well, on a graph, we would simply be looking for the x values of the points of intersection when both equations are graphed on the same set of axes. So now I will show you how both of these work in example 2a. So let's start with the algebra of 2a, and then we will go ahead and show you the graphical representation. So I begin this problem by letting f of x equal g of x as indicated to us in the directions of the problem. The next thing I do is I substitute the expression for the function on each side. So notice in black here, you'll see some brackets, and these are simply my explanations or my reasons for what I've done if it's not clear to you throughout the work. So let's go ahead and go further. Now we're trying to find, again, the x values that make these 2 equations equal. So we're going to have to solve this equation now that we have for x. The next step I take is to combine all like terms and get all like terms on one side of the equal sign, since I notice it's a quadratic. To solve quadratics, if you remember from Algebra 2, you'll always want them to equal 0. That's one of the easiest ways to solve quadratics. So now let's take it further. The next thing I notice is that every coefficient and the constant are divisible by 2. So when I do that to both sides, I end up with x squared plus x minus 12 equals 0. Dividing both sides by 2 made it easier for me to factor. So that was the next move. And remember, I'm not going to square root to solve this because there's an x squared and an x in the equation. So I asked myself, what two numbers multiply to negative 12 and add to 1? Well, those numbers were positive 4 and negative 3. So the two answers are x equals negative 4 and x equals 3. One thing I want to point out is we did not just find the x-intercepts. So do not write negative 4, 0 or 3, 0 because, again, we were just finding x values that made y values equal here. We didn't necessarily suggest that the y values are zeros. So let's look at the graph to get a better idea to confirm what these answers really mean. So to show you this, I went ahead and pulled up a free online graphing calculator from Desmos.com. You could use this at home, but also I've shown you some apps, or you may have your own physical calculator. But nonetheless, you need to graph both equations, and to do so, if you're on the TI, you'll hit the y equals menu, and you'll enter both of them. Now, in order to see the intersection points of these graphs, you're going to have to adjust your window a little bit. So notice I have my y max at around 20, and the y min is about negative 40, and you'll see the intersection points. And on your TI graphing calculator, in order for you to see these points that I'm seeing, you're going to have to hit this. You'll have to hit second button, then you'll have to hit the trace button, and this is actually taking you into the calculate menu. And then what you'll want to do is select the option that reads intersect. Now from there, you'll have to move your cursor around the points, both left and right, and hit enter a few times before they show up. And again, I can go over that in class in further detail if you're still having some confusion. However, notice what we said when we solved algebraically. We said our two answers were x equals 3, and we said x equals negative 4. However, our y values, as I suggested, were not zeros. Notice they're much different. Y is 3 in this case, and y is negative 32. So again, at these points, when we have an x value of 3, both equations will have a y value of 3. When we plug in negative 4 to both of these equations, both of the y values would equal negative 32. So please take a moment and try example 2b and have it ready to check tomorrow. We will now move on to objective number 2, which is associated with finding the domains of various functions. Now, we had mentioned domain in the previous lecture, and we're going to take a much closer look today in this lecture video and as well as in class. So let's start with the function f of x equals 1 over x squared minus 4. Let's answer part A together. It says, which x values would give a 0 in the denominator of the function? So if you can't just see it and it doesn't pop out at you what x value or values would make the denominator 0, then go ahead and just set up an equation. So I went ahead and did that and said x squared minus 4 equals 0. Well, what would the x values be? So I'll solve it and it will tell me that. So I added 4 to both sides. I went ahead and square rooted because there was only an x squared, and I get two values, x equals 2 and x equals negative 2. Part B then says, what is the result? What happens if you have 0 on the denominator? What's unique about that? Well, remember that you cannot have 0 on the denominator, and we call that undefined. Remember, if 0 is in the numerator, that's fine, but when it's in the denominator, we call that undefined. So what often confuses students is the various ways you can write your answers for domain. So in this case, there's only two values x cannot be. Remember those values from part A, positive 2 and negative 2? If I were to plug those into this equation, I would get 0 on the denominator, and that cannot happen. So the easiest way in this case to write the domain, in my opinion, would be to say x cannot equal positive or negative 2. So there's one way to write the domain, and again, I'll show you two other ways to do so. Another way you can write it clearly looks a little more complicated than the first way, but it is another way to write it. So notice if x cannot be negative 2, it can be anything less than that. And that's what this says as a compound inequality. X can be greater than negative infinity, but it's less than negative 2. Well, also, x can be any value in between negative 2 and 2 as long as it's not equal to either of those values, and that's what the middle inequality suggests. And finally, x can be greater than 2 as long as, again, it's not equal to 2, and that's what the third inequality says. So that's the second way you can write it, and finally, we'll do it with what we call interval notation. And again, the third way that I'm about to show you, that is the most common way you will see the domain written throughout this course. So the third way with interval notation, remember I mentioned this previously, is to take the inequalities that I've written above and kind of put them into ordered pair form, essentially. So notice negative infinity less than x less than negative 2 can be converted to symbols like so, with soft parentheses around each value. On the left, you'll see the minimum value, and in the right, in parentheses, you'll see the maximum value. Now, we use soft parentheses to indicate that we are not using equal signs. We are not equal to negative 2, therefore I will use the soft parentheses to indicate that. Notice all throughout the inequalities, there are only greater than and less than symbols, no equal to. So that's why all of these are soft rounded parentheses. The U's that you see instead of commas in between the parentheses, that stands for union. And union is a term that says we're going to put them together, right? We marry them together. So it's just, instead of writing a comma, we'll use the U for union. So either one of the three ways is acceptable for 3C. However, going forward, I want you to start to get used to writing your domains in interval notation as the one I have boxed here. So go ahead and try example 4A and B on your own, and we will check that in class tomorrow. Example 5 is asking us to find the domains of the given functions. And of course, I'm going to try and do this from an algebraic perspective and shy away from the graph, just to give you an idea that you do need to be able to do both. So I'm going to start with 5B. And I'm going to notice that, oh, this has a fraction and there is an x in the denominator. So once again, my question is, what values would make 3 minus x equal to 0? Now, if you can't see that, then you could solve this by writing an equation. However, I think this one's pretty straightforward. So if x is 3, we would get 3 minus 3, and that gives us 0, and we cannot have 1 over 0. So instead of writing x can equal 3, my domain can be written very simply as x can be any value at all except for 3. Now that's one way to write it. I'm also going to write it in interval notation, which is the preferred way from here on out. So I've written it in interval notation, and notice we start on the very minimum value of x would be negative infinity. Then we get to 3, and I can't include 3, remember, as we discussed earlier, so I'm not going to use a bracket, rather this soft parentheses, and then we union it with 3 to infinity. So this union is kind of the indicator that we're not going to use 3, we're going to use every value very close to 3 on either side. So 2.99 would work, as well as 3.01. So no matter if it's really small, or smaller than 3 or larger than 3, as long as it's not 3, we're good to go. So let's try example 5D, and we have the function h of x equals square root of x minus 16. Well, if you recall from earlier, square root functions cannot be negative underneath the square root symbol. So that means the expression x minus 16 cannot be negative. Well, if it can't be negative, it could either be 0 or it could be positive. So that's what I've written in the inequality here. X minus 16 must be greater than or equal to 0. Now, to solve that, we simply add 16 to both sides, and we end up with x is greater than or equal to 16. So there is one way to write your domain, and notice I did not write it with cannot equal because in this case it makes more sense to write it in terms of what x can be as opposed to what it can't be. There are several more values that it can be, so we'll just write it this way. Now, I would also want to show you interval notation because again that's the preferred way to write it going forward. So take a look at the interval notation to write the domain, and notice I have a bracket next to 16 instead of a regular parentheses, and that's to indicate that we can include 16. 16 is actually a number that is part of our domain. Since it's equal to, we will signify that with a bracket as opposed to a soft parentheses. So notice I have 16 comma infinity, 16 being my minimum value of x that we could possibly use, and then infinity being our upper limit. So I'll try one more with you, and then you can try the rest on your own. So notice the function in 5e has a numerator and a denominator, the numerator having a square root and the denominator being t plus 6. So remember, this kind of puts together the last two examples in one. So we cannot have negative values underneath the square root, so I'll write 7 minus t must be greater than or equal to 0. When I solve that, notice I would get negative t is greater than or equal to negative 7, and then to get t alone, I would divide both sides by negative 1. Remember, though, when you do so with inequalities, the symbol switches its direction. So now I get a statement that says t must be less than or equal to positive 7. The denominator, remember, we cannot have 0 in the denominator, so I will write an equation that says t plus 6 cannot equal 0. To solve this, I will subtract 6 from both sides, and it tells me that t cannot be negative 6. So when you put these two things together, notice what it's saying. We can have any number less than 7 or less than or equal to 7, provided that it's not negative 6. So let's go ahead and put these into interval notation and complete the problem. So I've written it in interval notation, and notice I start with the very minimum value of x, and that is, of course, if we can be less than or equal to 7, then negative infinity is our very minimum value of x that we could use. And then we stop. We do the union when we get to negative 6 because we cannot use negative 6. So that's why you see the soft parentheses. We take a break at negative 6 on either side, and then notice 7 is our very maximum value of x. So that maximum value of x can be included. We can equal 7, so we put a bracket around it, and you have your domain. So go ahead and try the rest of the examples or exercises, from example 5, and check your work tomorrow in class. Also, please take a moment to look over the things we've done here and write at least one question you have after watching this video lecture and taking some notes. Well, that concludes video lecture number 7. Thank you for watching, and good luck.